Welcome. Another meeting of the Heart of Illinois Wastewater Operators. This morning we've got three presentations lined up. The first presenters are with Industra Filters. We've got Rob Geyer and Doug here. Rob's our Illinois, Indiana. Doug's the Wisconsin area. So we'll turn it over to them and get things started.
Thank you, Kent. Bear with me while I accidentally turn the mic off and try to hook everything onto my shirt. Oh, yes, sir. All right. I think everything's on. I think everything's close enough. Firstly, I want to thank the Heart of Illinois for having us here. I want to thank Kent for reaching out and helping everybody set this up, and thank you to everybody for being here. I'm going to grab the clicker because I forgot to do that. And now we can begin in earnest. I'm Rob Geyer. I'm with Industra Filter Manufacturers. This is Doug Visnak. We're going to be discussing optimizing blower filtration for reliability, efficiency, and value. Blower filtration is something sort of generally overlooked. Engineering, operations, management, it's something you don't think about until it's a problem or until a blower's broken. If there's one mission we have, it's to get people to think about things from the outset. There's a number of consequences, good and bad, to the right and the wrong sort of filtration.
First of all, good morning, everybody. I'm seeing all of you for the first time. It's nice to meet you. My name's Doug Visnak. I'm really glad to be here. I'm going to go over the agenda for today so we know what we're going to talk about. First, we're going to do a brief company overview, talk about who we are and what we do. I'm going to give us a rundown on the presenters, so a bio on me and Robert. And then we're going to be talking about optimizing intake filtration and what constitutes an optimized filter. And then we're going to talk about effective filter maintenance, common practices, best practices, things we see most often in the field, things we recommend. And then optimization consequences. Consequences is kind of a loaded word, but in this scenario we're talking about the positive consequences of proper filtration. Brief company overview. We are a family-owned small business based in Indiana, Cherville, Indiana to be exact. I have been since 1971. We have an in-house design team with more than 50 years of engineering experience for filters. We are also dedicated to high quality, reliability, on-time delivery. Having a filter that does what it says it's going to do, it's going to protect your machine, and getting you those filters on time.
I'm Rob. I've been with the company. I spent about a decade on our factory floor. I've been on the road for 5-ish years since then. I am a little older than I look, but it's also a family company. You can start working when you're 8, so long as they don't pay you.
And I'm Doug Visnak. Technically, I'm a business developer. I began working with Industra in 2023, so last year, and I primarily help improve air filtration at wastewater treatment plants throughout Wisconsin, as well as doing presentations at wastewater operators associations such as this.
All right. So that gets us into choosing the right filter. And our subtext here is outdated, functional, and optimized. Outdated being something that probably doesn't have any place in modern wastewater treatment. Something that's actively detrimental to your operations or to your blower. Functional is the filter does what it's supposed to do. You've got the bare minimum. It is an option. And optimized being the best case scenario for operations, maintenance, and machine longevity. With that, what's an optimized filter? You guys are going to hear the word optimized 1,700 times today. We may as well discuss what it means. To us, the filter guys, an optimized filter is one with a modern synthetic filter medium. It's not going to disintegrate if it gets wet. It's not going to swell up in humidity. It's got a combination of service life and efficiencies, machine protection. From there is zero bypass design. What that means is that all of the air entering a filter housing exits via a filter element. The primary purpose of a filter is to clean air going into your machine. If dust, particulate, ingress is going around or through your filter, you're not fulfilling the primary purpose of that filter's existence. So for a filter to be a filter, for it to be optimized, it has to actually clean the air. A low initial restriction. So you're as low possible delta P as you can get. That, in the long run, means longer service life. That means less energy consumption. That means less maintenance, less inventory. Long service intervals for all of the above. Resistance to freezing, resistance to weather. I'm very familiar with the weather patterns of the Midwest. It gets wet, it gets cold, it gets hot. You need a filter that's not subject, victim to whatever's going on outside. Finally, optimizing filtration optimizes blower performance. You've got your PDs and your multi-stages they're the same thing they always were, and they're brilliant machines. But as we move on into the 21st century further, we're seeing high-speed turbo blowers and single-stage integrally geared. I have so much trouble doing that. I like to walk around while I'm talking. As newer machines come out, newer technologies, newer filtration, 21st century filtration is required to keep machines running the way that they're supposed to run and keep them working as cool as they're supposed to be. With that, we're going to begin with filter media, the guts of a filter element. With our outdated medias is wire mesh. Wire mesh is outdated for a number of reasons. Back in my dad and my grandpa's day, when a good portion of wastewater treatment plants were still coarse bubble diffusion, wastewater was fine. Your diffuser was a pipe with holes drilled into it. You're basically a bubbler like in a fish tank. Didn't really matter. Particulate going through the diffuser kind of went through the diffuser. It wasn't a big deal. Today, with rubber and ceramic discs, you can take a 120 lumen flashlight, shine it on one side of your diffuser disc, and light's not going to come through the other. If you have particulate going through or around your filter, into your machines, into your pipes, into your valves, that's going to wind up in your diffuser. Your fine bubble filtration becomes more and more and more coarse, and I'm willing to bet all of you know what goes into draining and refilling a basin much better than I do. I'm told it's not that fun. Moving on to functional, we have paper and polyester. So wire mesh was as popular as it was and continues to be popular because it lasts forever, right? The reason it lasts forever is because it's not very efficient at all. A very good wire mesh media will be rated 60% efficient at AC fine dust. That's Arizona crusher dust. That's just a test dust. But that means it's picking up 60% of road dust. It's not picking up anything micron rated. It's not stopping, your bug parts, your solids, your dust moving through the air. Paper and polyester are probably what I see outside of wire mesh, what I see the most when I'm on the road. And they you lose the longevity that you have with wire mesh, but you actually have an efficient media. Paper and polyester both are very inexpensive, very efficient. I've seen papers get all the way up to 95% efficient at 5 micron. Problem with paper is you have no environmental resistance whatsoever. On a very, very humid day, I've seen paper filters in train water swell up and collapse. You have driving rains, you have a lot of snow. I've seen paper just rot out of the element. Polyester, again, is very, very efficient, but you don't have the longevity of wire mesh. It tends to be heavy, and with scrims and fewer pleats, there's less media, there's more restriction. That brings us to the optimized options, which are modern synthetics. 21st century synthetics beat that filtration compromise. You're approaching the longevity and the service life of wire mesh while still having a range of variable efficiencies like with paper and polyester. On top of that, since they're a completely synthetic media, this isn't cellulose, this isn't paper, they're not going to swell up when it's humid, they're not going to disintegrate when they get wet, water runs off instead of gets trapped. So your optimized option is a modern synthetic, a filter you can run for a very long time, but also actually protect your machine with. From there, styles of filter. For us, and this is an 80s era industrial panel housing, panel filters are outdated for a number of reasons. For one, a single panel filter has less usable surface area than a comparably sized cartridge filter. It's 2D instead of 3D. There's just less media, there's fewer pleats. That's less dust holding capacity, that's less service life. On top of that, it's essentially mechanically impossible to seal a panel filter. Half the panel filters we run into in the field don't even have gaskets. They're sitting in a frame or they're sliding into a channel. Even the ones that do have gaskets, because there's 4 sealing surfaces on this, it's very, very difficult to actually clamp it down, to get a gasket compressed all the way down on all 4 sides. I'm sorry, man. I'm going to do that the whole time. I apologize. So because there's so many sealing surfaces, because they're the way that they're seated into a panel housing, they leak. Air gets through them, air gets around them, and that's just part of the joy of panel filters. There's not much you can do about it. We quit making panel filters in the 90s because we couldn't make one that didn't leak. On top of that, these are very high restriction. Air is a fluid, just like water. Fluids don't like hard turns. They don't like right angles. With a panel housing, what you have here is a very small orifice, so you've got quite a bit of airspeed velocity going into this, and then you go right into a flat surface and right into a 90-degree turn. Because of those sharp angles, because of those hard turns, because of those flat surfaces, you actually actively reduce your blower's energy efficiency. You need more drive, you need more runtime, you have to work the machine harder to get the same amount of air through it. Panel filters are outdated, they leak, they don't work very well, and they make your blower work harder than it needs to. That takes us to functional. And this is probably the most familiar thing in the room, cylindrical cartridge filters. These can be open metal ends, these can be open molded rubber, these can be open-closed, one open end with a gasket. And these have, compared to a comparably sized panel, a much increased dust holding capacity. It's 3-dimensional, there's a lot more media, there's a lot more pleats. You're getting more out of this than you would a panel. This also reduces bypass. You go from 4 sealing surfaces that you can't seal to 1 or 2 sealing surfaces where you have a better chance. However, these are still high restriction. What we have here, our little infographic from, I believe, the 70s here doesn't accurately show how air moves through a filter. It doesn't very gently roll through. It's crashing up into that seal plate, crashing through there, and then again going right down to 90. That's a lot of turbulence, that's a lot of sharp turns, that's everything that creates inlet restriction. So these are functional in that they are filtering the air going into your machine. However, they're still reducing your blower's energy efficiency, and there's no guarantee of zero bypass. Bringing us, sorry, one second. My throat feels like it's made of sand. Oh, and I've ruined everything. We're pros, can you tell? That brings us to the optimized option, conical cartridge filters. With a conical cartridge filter, with both the shape of the filter, the amount of pleats, you've got a lot of media, you've got a lot of dust holding capacity. That extends your service life, that's less inventory, that's less maintenance, that's less demand on your machine. Again, because of size and design, everything on here is curved. With a conical cartridge filter, you are removing the sharp turns, you're removing the flat surfaces, you're removing the hard angles. Air flows through a filter instead of crashes into it and then gets forced through by your machine. And again, we get excited about fringe benefits. The most important part of an optimized filter and a conical cartridge filter is that it is zero bypass. These have one sealing surface and a closed end. Once you crank down and get this sealed up, you compress that gasket very, very well, and all of the air entering a filter housing exits via the filter element. Air is being cleaned before it goes into your machine. On top of that, because of the extended service life and the low initial restriction, users tend to see a 1-year return on investment, just in power savings alone from reduced blower demand. Questions thus far on medias or styles of filtration? Sorry, medias or types of filtration. Yes, they can. We don't recommend doing it a lot. Yes, sir?
I want to repeat the question.
Oh, sure. He asked if modern synthetics can be cleaned and reused. They can. We recommend blowing out with compressed air. You can get quite a bit of life out of that.
On the inside out too, so you're not
Yes.
any particulate.
We don't recommend soap and water, and we'll actually talk about that in the next section. but you can extend, yes, you can extend your life a little bit. We don't recommend getting any kind of filter wet. Thank you. Any other questions, I suppose, before? Yes, sir.
What about lower mixers on the oxidation business? Would you recommend, because we use a water mesh type of thing out there, and we've had one, it seems disappointing, particularly this bad snow or whatever, we have to shut it down because it's blocking. Do you use those type of filters outside like that?
Mm-hmm. Absolutely.
Yeah, I thought they were.
So he asked, and forgive me if I'm wording this wrong.
I didn't know about that.
No, it's not a dumb question at all. I believe basically you asked if these are fine for outdoor use. Yes, absolutely. And from an engineering standpoint, we recommend having your filters outside so that your building doesn't act as a filter and you don't have to worry about shortages with makeup air. I got to be in a blower room once where a guy shut the door, turned the machine on, didn't have the roof hatch open, and all the doors slammed shut because we created a vacuum. You eliminate that when you have all your filters outside. Thank you. That's an excellent question. Anything else? I'm having fun. All right. Got to talk about inappropriate filtration while we're talking about optimized filtration. For us, that's HVAC filters, tuck-in filter pads, automotive filter elements. Particularly with pads and with HVAC filters, these are inexpensive elements. However, they very consistently increase operating cost. We talked about panel filters not sealing. You can't even pretend to seal these. With your average HVAC filter, you got a beverage board frame. And a motivated individual can take a beverage board filter and just accordion it in their hands. I've done it accidentally with my home HVAC filters more times than I care to admit. With a tuck-in pad, what you have there is a sheet of polyester batting, horsehair, it's flexy. You stuff it into a frame. There's no means of sealing that whatsoever. And you can see on the outside here, the edges of this are dirty and the center's more or less clean. Air always follows the path of least resistance. Dirt fills up the edges of this. Why is air going to go out of its way to go through the middle? It's filling up the edges, bypassing and going straight into the machine. What this means for both of these, low dust holding capacity and constant bypass. Ingress going into your machines over and over all the time, 24/7. This wasn't as big a deal. It's not as big an issue with PD blowers or multi-stage blowers because they're tough. They're steel fan wheels, they're steel lobes. With modern machines, high-speed turbos and single-stage machines, where you have a machined aluminum impeller, exposed electronics, crazy high RPMs, flooding your machine with dust 24/7, it chews itself apart. It's the best way to break a turbo blower. With these, you have frequent maintenance. Lots of replacement, lots of cleaning. Wastewater treatment plant out west in Oregon had these tuck-in filter pads on their turbo blowers. Box of these pads was $1,200 about. They were spending almost $10,000 a year on these. And I don't know how much time in labor and freezing outside power washing these out. Again, these inexpensive, cheap and easy things become very expensive when they break machines, but then the costs add up when it comes to replacement and when it comes to how much time you're outside with a hose. Again, you consistently damage your machines and your process. Breaking a blower is very expensive. With inappropriate filtration, you're allowing bypass. This is the outside of an open filter element. That's what they look like. They get pretty filthy. Give you kind of crawlies a little bit. Problem with this is the inside of this filter looks just as bad as the outside. That means particulates moving through or around that filter media, and again, going into your machine, going into your pipes, your systems, going into your process. With bypass, with dust ingress, you break a machine. These are the guts of a failed airfoil-bearing high-speed turbo machine, and just looking at it, you can tell some things are wrong. The sand dunes in the bottom of this machine aren't supposed to be there. These brown cords up top are supposed to be red, and all of these desert camo parts are supposed to be white. This machine failed a couple of months outside of their factory warranty. It was a bit of a nightmare to fix. So again, They were opening up their blower enclosure to shop vac it once a month. The only person that should be opening your blower enclosure is your blower technician. You know, the guy from your manufacturer. Bypass and dust ingress also leads to VFD failures. They overheat, they melt. All of this is energy costs, and all of this is machine costs. This particular machine here, after they failed outside of warranty, they had to have a technician from the factory come to the plant, disassemble the machine, palletize it, ship it to country of origin for repair, and the entire time this was out wherever it was, they had to rent a multi-stage blower to meet their redundancy requirements. In 2020, when I first asked what it costs to rent a blower, it was $6,000 a month or more. I imagine it's worse now. But because they weren't filtering this machine and they filled it with dirt, they ended up spending well over $100,000 to get everything back in place. It was like a third of the cost of the machine. The entire time, that's downtime, that's just money, 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 and work. And it's preventable by optimizing filtration. Just about wrapping up inappropriate filtration, we have impeller erosion. So this isn't a machine failing, this is just a machine wearing down. This is from an independent plant study in Coachella, California, I believe. And they found that with machines with eroded impellers due to dust ingress, we're using an additional 5 kilowatt hours of power compared to machines that weren't. I did this math a long time ago when the U.S. national average for municipal power was 7 cents. It's closer to 12 or 13 now. But an extra 5 kilowatt hours at 7 cents a kilowatt is over $3,000 a year. So their 21st century modern machine, after you chew up the impeller and you fill it full of dirt, suddenly isn't all that energy efficient. It doesn't work the way it's supposed to. So optimizing filtration keeps machines running the way they ought to. On the right here, this is actually a machine I got to see. I don't remember what exactly they did, but they filled their inlet with some sort of metal shavings or washers or something. Obviously didn't have a filter on it. These blades are razor sharp. You know, it's a machined aluminum impeller. It's not as tough as steel. So they chewed this impeller all up, and it still moves really, really fast and makes a lot of noise. But because they chewed this impeller up, that machine's not capable of compressing air. They've got a turbocharged food processor that doesn't actually compress and move air through it. That was entirely preventable with filters, and I think they just weren't using one at all. So again, optimized filters prevent impeller wear and keep machines running the way they're supposed to. That wraps up inappropriate filtration. Do we have any questions? All right. Doug's going to take over here for a little bit because, again, I'm very dry right now.
All right, so now we're going to be talking about filter sizing and optimization. Common practice is buying the cheapest and smallest filter for your blower. And that's fine in most applications, but for an optimized one, not so much.
By cheapest or smallest, we mean putting a filter rated for 1,000 CFM on a blower that's pushing 1,000 CFM.
Correct. An optimized filter sizing is going to extend your service life and reduce power consumption. We typically say that an optimized filter sizing is 1.5 times your rated CFM. Here's a couple different configurations that we have for orientation that can help reduce maintenance time and ensure operator safety. The right filter orientation can make maintenance safe and easy. Ooh, too fast. Here on the left-hand side, we have a top mount filter, which is mounted directly to a blower.
Bottom outlet.
I'm sorry, bottom outlet filter, which is mounted directly to a blower. And you can see that they have no extended piping. It's mounted directly to a blower. It's probably the best application for a bottom mount filter.
This works for direct mount to a blower. This works for, we see these a lot on roof penetrations. If you have an elbow coming out of the wall just low enough, this works. But I'm already 5'6". So if you have I can't walk over there and demonstrate. If you've got a pipe center that's 6 feet out of the wall, you know, your wall penetration, you put a long radius elbow on top of that, and then a filter on top of that, suddenly your access is 12 feet up in the air. They're great for what they're great for, but there's other options.
That's why we have top mount options. So if you have a pipe center that's maybe 10 feet in the air and a flange that's not very long, having a top mount filter is going to make servicing that filter at grade much more easy.
So you're looking at a 10 to 12 foot pipe center here. If you can't elbow up at a 5 or 6 foot pipe center, you certainly can't elbow up at 10 or 11 feet. All of a sudden, your access is 18 feet up in the air. Rotate an elbow 180 degrees. Have a filter that you can walk under and service at grade.
And for those in-between heights, we have side mount filters. Sometimes they're supported with stanchions. Most times they're supported with stanchions. But these are great for for walking up and servicing these at grade. And again, because of the synthetic media that typically goes inside these filters, you don't have to worry about grass clippings or rain or anything getting inside your filter and affecting your process. Again, different types of orientations, and even for larger manifolds. Sometimes we can replace panel filter housings with 2 cartridges. Here's a bottom outlet filter that is taking the place of the original panel filter housing, and there's only 2 cartridges inside. Here's a side mount filter with a screen in front of it, a couple stanchions, and again replacing a massive panel filter housing which can have anywhere between 8 to 16 panels inside of it. Again, 2 cartridges. And then here's a very, very large manifold. I believe this is a 36-inch flange. It's massive. 4 cartridges inside. And then this is in an area that is actually very, very prone to big storms and hurricanes, so there's a little bit more of a support underneath.
Yeah, they have the hurricane-proof legs.
Again,
I don't know if they're hurricane-proof or not, but
these are all making it so they're easy to maintain and serviceable at grade.
so especially with these manifolds, these larger options, optimization is a scalable technology. It works if it's a 4-inch pipe. It works if it's a 60-inch pipe. There's an option. Most of these replace big old giant panel filters, like Doug said, where you were looking at 12, 24 elements. You cut it down as far as you can while still reducing your energy consumption and your demand.
Freeze discouragement. So restriction. We talked about restriction earlier and how important that is to maintaining your machine's efficiency. Well, freezing can cause an increase in restriction. Filter freezes, or freeze discouragement is best practice. We're going to get into freeze discouragement a little bit later on when we talk about benefits of optimization.
So, again, summing up what an optimized filter is, relates to everything we said. It's a filter that doesn't leak, starts with as low a restriction as possible, lasts as long as possible, and resists the elements.
Next, we're going to be getting into effective filter maintenance. So we're going to get into common practices, best practices, things that we see most often in the field, and again, the things that we recommend.
So, we had a question about filter washing earlier. When we say washing here, we mean getting this filter wet and drying it off. Not necessarily blowing it out, shaking it off, totally fine. But washing your filter, getting it wet, adding a detergent, adding water, is harmful to the filter and to the machine. Every time you wash a filter, you lock particulate in that filter media. You transfer particulate from the dirty side of the filter to the clean side of the filter. We had an old salesman, my predecessor, and the way he worded it was dirt and water make mud. If you encase something in mud, something's sticking around even after you knock it all off. Every time you wash and clean your elements, you render them less effective. The efficiency goes down, the service life goes down, and you're also exposing your machines to ingress. Every time you wash a filter, you permanently increase your initial restriction. You permanently increase your energy costs. A representation of that here, say you're starting a filter at 3 inches of emission. It's 3 inches of initial restriction, 3 inches of water. You run it as long as you run it until final. You clean it, you put it back. You're not starting at 3 inches. You're starting at 4, you're starting at 5, you're starting at 6. Eventually, that initial restriction climbs every time. Eventually, your service life is reduced to the point that why are you washing the filter? With an optimized filter, you're seeing 6 months or, depending on media, 6 months plus or a year plus of service life. You end up reaching a final restriction well before you even think about having to clean it. So, especially for cottonwood, harvest, construction, when things are pretty bad, shop vac it out, blow it out from the inside out, no problem at all. We really don't recommend washing. More on common practices or filter changes. So when we ask people when do they change their filter, when do you know to change your filters? They say they change on a schedule. which is not bad. They say we change when it looks dirty, which is my personal favorite answer. Because, I mean, you leave a filter on the shelf out in the garage long enough, it starts to look dirty. Or they say they wait as long, and waiting as long as possible. And all of these make sense and have their benefits. However, waiting as long as possible, and we're going to discuss this shortly, means you're running your restriction up as high as you can. And when you run your restriction up as high as you can, you run your power bills up. Changing on a schedule is a very safe way to change it, truth be told. You know when cottonwood season starts, you put a new element right in before that. You know when the winter's about to end, you pop a new element before that. The problem is with changing on a schedule, you could be leaving a filter in way too long, and again, approaching the risk of collapse or driving up your power bills. You could also be leaving money on the table, changing something sooner than you need to and buying more filters than you need to. Changing when it looks dirty, the exact same problem. A lot of times that means taking it out too soon. A lot of times that means, it doesn't look that bad, and then accordioning your filter. The best way to know when to change your filter, different slide. I think my boss might have moved our orders around. The best way to know when to change your filters is by monitoring differential pressure. This can be with a gauge on the outside of the filter. This can be with the SCADA system in your machine. But knowing exactly where your filter's at and restriction-wise is the best way to know when to change. You know you're not throwing it away too soon. You know you're not leaving it in too long. It's at 8 inches. It's time to throw it away. More on filter changes, and this is really where we're going to break down the relationship between service life, initial restriction, and energy costs. It's a little dry. I apologize in advance. So again, common practice is waiting as long as you can, which makes sense, really. I don't want to buy more filters. We'll get as much life out of this as we can before we have to spend the money. However, in the last third of a filter service life, between 6 to 10 inches of water, is where you see the most filter-related power consumption. A lot of times, the cost of your energy is exceeding the cost of your filter elements. Changing a filter, an optimized filter, at what we call the sweet spot, saves money on power while still ensuring close to or over a year of service life before you change it. Something to note with all of our math and our life cycle comparison here, an inch of water column is 3.5 to 5 kilowatt hours. That's close to $3,000. 6 inches of water column is 20 to 30 kilowatt hours. That's a lot more. 8, 10 plus, everything scales exponentially. So with that, we have a traditional intake filter where you're starting at an average of 3 to 4 inches versus an optimized filter where you're starting at a ½ inch or less. Something to note here, starting here at a ½ inch versus starting here at 3 inches, assuming you operate 24/7 and these are magic filters and the restriction never ever goes up, the filter starting at a ½ inch a year is going to be $3,000 to $6,000 cheaper to run than the filter starting at 3 just because of that initial restriction. Now, the other thing to note is that starting as low as possible means it loads as slow as possible. That filter lasts longer than it would just because of that low starting point. So, again, that ½ inch takes much longer time to reach. So, like we said on the last slide, the most filter-related power consumption occurs in the last third of the filter's life. If you have a filter element that you are changing 3 or 4 or 5 or more times per year, that means that 4, 5, 6 times a year, you are seeing a massive spike in power consumption that wouldn't be there otherwise. With an optimized filter, starting as low as possible, you tend to see a year or more before you even reach 6 to 8 inches. At that point, you've had your filter in for a year. You can throw it away before you reach that last third and spike your power consumption up and still not be down money. It's, I guess do you want to spend money on filter elements, or is it NIPSCO up here? Or I don't know who the utility provider is for the area. Gotcha. Do you want to spend money with the utility provider, or do you want to buy a new filter element, is what the question comes down to. But starting as low as possible, building as slowly as possible, is the best case, the best compromise between running a filter as long as you can and not driving your power bill up. Wrapping this up here, An inch of water column, again, being 3.5 to 5 kilowatt hours. In our life cycle comparison here, you could see a first month savings of $200 to $300, a second month savings of $600 to $800, third month savings in the thousands, and a first quarter power savings of $2,000 plus. And that's just based on the very limited math that I was able to do for that graph. Again, also assuming a wildly inaccurate 7 cents a kilowatt hour. I really need to redo all of the math for this, but I forgot how I did it in the first place, and I haven't had much time for algebra. Questions? That's a lot of information in a pretty small slide. All right. Furthering best practice is freeze discouragement. Illinois gets cold, Indiana gets cold. We're all pretty close to a body of water at some point or another. Filter freezes happen. Filter freezing is essentially a differential pressure spike. It's not that in practice, a bunch of snow, a bunch of ice gets pulled into a filter. That's particulate. That just means a massive, fast increase in restriction as opposed to a slow, gradual one as it builds. So, again, with our math, in a single icy week, right, maybe you don't have an alarm. Maybe it doesn't freeze completely and fail, but you still increase your restriction overnight and then decrease your restriction during the day as it warms out. What that means is you're seeing that big last third spike in power consumption 4 or 5 times a week instead of once every few months. Filter freezing isn't just, oh Lord, I have to drive to the plant at 4 o'clock in the morning and change filter elements. It's also a giant increase in the amount of energy you're putting into aeration. Having a freeze-resistant filter or having dedicated freeze discouragement measures is best practice because it keeps operators safe, off the road when it's icy and horrible, and it keeps that giant spike that keeps your power bill from looking like an EKG. So with this single icy week, with this model, they saved over the model saved over $500 just by preventing that up and down spiking. Finally, and I need to move this order back, differential pressure monitoring is the single best way to know when to change your filter. You know exactly how much dust you got in there. You know exactly how much life you have left on the element. It's not guessing on your schedule. It's not risking a collapse. Do we have any questions on best practice versus common practice in maintenance? All right. Is this still me or is it you? Okay.
All right, so we're in the home stretch here. All right, we're going to be talking about benefits of filter optimization, or consequences as we called it earlier. Well, we talked about how it protects your equipment, right? It prevents impeller erosion, it prevents blower shutdowns, it prevents a belt ripping apart, things like that. An optimized zero bypass intake filter is going to protect your blowers, and that's the primary goal of a filter. Saving your power. Here is from St. Charles, Illinois, I believe.
This is St. Charles, Illinois, yes.
This is an amp meter that you can see this original black line from where their power consumption normally was at, and after putting in an optimized filter, it jumped down significantly.
So you throttle your input and output pressures on a multi-stage blower. After optimizing their filtration, they moved where their pressures needed to be back, and upon installing and throttling, they saw a 19 amp reduction day one in power usage.
That's thousands in energy over time. At 9.7 million gallon per day, saw a 19 amp production. That's pretty big. That's pretty huge.
We had mentioned earlier a 1-year return on investment. St. Charles recouped their initial investment in 114 days. Just how much restriction they reduced by installing got to the point where they recouped their investment while still protecting their machines, reducing their maintenance and their inventory.
Reducing maintenance. Optimization eliminates enclosure cleaning. It reduces the element change frequency, and it eliminates the need for ladders and man lifts. This is from Eugene, Oregon, where they had this legacy equipment with these really, really tall panel filter housings, about 5 or 6 of them. This is a day's work, getting up and down on ladders, changing all of these panel filters. There's about, I think 3 on right here, right? And
So there are 12 slots per
Yes.
housing on these panel filters. Each one of those holes has a pre-filter and a final filter.
right, so double
Each
that.
of those housings is 24 filters. The topmost filter is 16 or 17 feet up in the air. This was 2 or 3 days of labor.
Yeah.
This was guys going up on ladders and man lifts all day, switching filters out.
Not to mention dangerous. I hate heights, and I hate getting up messing with filters.
I watched Doug get on a lift this week. I can attest.
So, and then here in the foreground, we have an optimized filter, a side outlet filter, a couple stanchions, with 2 cartridges that's taking the place of one of these whole panel filter housings. Not only that, but I can walk up and service that at grade. I'm not that big. More benefits, weather stability. I think Rob might want to take over a little bit on this because he has a little bit more knowledge on this.
This is Herscher, Illinois. I'll take the clip.
Sure.
on that. They didn't have a freak ice storm. It wasn't horrific weather. This wasn't the polar vortex from back when I was in high school. This was just a cold night. Operator got to the plant in the morning, saw that his restriction had jumped up to about 2 inches and thought, that's weird. They're brand new filter elements. He popped the hoods off of these, noticed that they were just crusted with snow and ice, but because it is a modern synthetic media, it's hydrophobic and weather stable, the snow and the ice was dirt instead of something that froze the filter solid or completely filled it up. Operator, when this all happened, knocked the snow and the ice off the elements, continued to run. Restriction went down just to about starting, and he ran these filters for 18 months before he had to replace the elements. But your weather-stable media provides a better inherent freeze resistance, the potential for dedicated freeze discouragement, and turns what usually is a nightmare very early morning call into kind of a fun story. Is this me or you?
That's you.
Okay. More on freeze discouragement. You're minimizing early alarms. You're reducing that nightly, weekly high restriction power consumption, and you're making your life sort of generally easier. The bottom here, this is Soldotna, Alaska, which I'm not sure why people live there. They see an average annual snowfall of 80 inches per year. They spend 5 to 7 months of the year at 20 below zero. That's where, and this is a conversation for a different day, that's where dedicated freeze discouragement comes into place, where it's not an if, it's a when. But with that, very much the home stretch. Optimizing filtration is advantageous for, I'm trying to remember out these flags, advantageous for any machine type. So positive displacement blowers, PDs, nowadays they're coming out with variable speed PDs, and they're fascinating machines, but a traditional PD blower is on or off. You run it till you hit your DO, you turn it off. And again, it's a steel screw or a steel lobe. They're robust machines. They're not going to break because you get some dust in them. However, if you reduce your initial restriction as much as you can, you're moving more air through that machine than you would. You're reaching dissolved oxygen levels faster than you would. You're turning your machine off sooner than you would. The best way to save money on any machine in any industry is to turn it off and not run it. With multi-stage blowers, you can turn them up and you can turn them down. You can throttle your input and your output pressures. When you reduce your initial restriction as much as you can turn that machine way down. You can set it way back. That means less runtime. That means less horsepower. That means less demand. All of that's energy savings. And with modern machines, high-speed turbos and single-stage integrally geared, these are brilliant machines. They are inherently energy efficient by design. But aluminum impellers, exposed electronics, crazy high-speed movement, very, very tight tolerances on all the moving parts, they can chew themselves to death if you're not filtering them. So what's the advantage for optimizing filtration on a modern machine? You keep it running. You don't have to pay to fix it once you're outside of warranty. You keep it running the way it's supposed to run. On top of that, despite being very energy efficient, you can still turn these up and turn these down. You can reduce your speed on these machines. When you reduce your energy efficiency, when you reduce your inlet restriction, you reduce the demand for the blower. You turn speeds down. That's you turning the power bill down. But even with older technologies that are very, very robust, very tough, with newer technologies that are inherently energy efficient, optimizing filtration is advantageous regardless of what you happen to have in your plant. And now wrapping up, filters is a plant upgrade. We're always trying to reduce energy costs. We're always trying to get our power bills down. We're always looking at new opportunities. Traditionally, a lot of people's first move for reducing aeration costs is new machinery, high-speed turbo blowers, energy audits, projects. When upgrading a filter, it's very low impact, it's very low starting costs, there's no need for engineering, for grants, for construction. You can save thousands of dollars without any of the work, any of the hassle, any of the purchase. We're not disparaging engineers or engineering projects. What this does is a low-cost, low-impact energy savings upgrade that frees up time and money for the myriad other issues that wastewater operators run into. Picture here, this is Whispering Palms. This is a tiny, tiny rural community in California that was drowning in energy bills. They had 3 multi-stage blowers that they were running 24/7 at capacity. They were getting in trouble with their local governing body because they didn't have their redundancy requirement on aeration machines. They were using more power than they thought possible, and they'd begun the process of engineering and applying for grants to buy a high-speed turbo blower. They optimized their filtration instead and reduced their energy costs and their operations dramatically. Nowadays, they run 1 multi-stage blower as a primary, they have 2 on backup, and they scrapped their plans for buying new machines, all for literally an accessory purchase, without tearing down walls or pouring concrete pads or sitting through engineering meetings. So optimizing your filters keeps your machines running, cuts your power bills down, and saves time and money for other things. With that, thank you again, everybody, for being here, for bearing with us, for watching me fumble with a clicker. We appreciate the opportunity, and if there's any questions at any point, we're more than happy to answer.
Thank you.
Yes, sir.
Do you have service or capability of doing energy audits? There's a lot of grants or opportunities for energy efficiencies, upgrades through AMR, as well as other.
We've had people reach out to us here and there. Nothing's ever happened yet, but we're always happy to participate. Any other questions? All right. Thank you very much, everybody. Thank you, Kent. Appreciate it. Oh. There's that. Thank you kindly.
Yep, thank you. Okay, we're going to take 5 minutes to get things switched over between presentations, and then we'll be back. Okay. Sorry about that. I didn't have the mic on. Is yours on, Robert? Push and hold.
Oh, push and hold. There it is. Okay, great, thanks.
All right. Robert's here with Water Treat Technologies to do a presentation for us for algae control for lagoons. So we'll go ahead and get started.
Oh, oh. There we go. Okay, great. Hello, my name's Robert Risley with Water Treat Technology. I'm a Class 1 operator, industrial engineer, and I've got about 30 years in the wastewater industry. So, Water Treat Technology, we do a lot of different things. We're contract operators, so we got about 30 clients that we actually take care of their lagoons and wastewater treatment plants. Plus, we also have, we do the laboratory, we do the DMRs, we do everything as far as that related to contract operating goes. So, the other thing we do is we help other locations. As a consultant, we basically go to your site, help you look at what you have, not just lagoons, but also activated sludge, anaerobic digesters, and that type of thing. So we actually have another side of the business where we actually make our own bacterial products for lagoon sludge removal. And we're also distributors for nanobubble technology, aeration, and also the ultrasonic technology for algae reducing. I'm going to step up this way. I hope that ain't too close for you. But the first step to controlling algae is to be able to identify what type of algae you actually have. There are basically three types of algae that we'll be identifying today, and these are the most common that I see in the wastewater industry. There's filamentous algae, plankton algae, and macroalgae, also sometimes called char algae. Oops. Filamentous algae is often called horsehair or mat algae. It basically forms on the surface of the lagoon. It's kind of long and stringy, and it's actually one of the easiest to treat and to control. And if you can look how, this is basically, let's see, this might be anyway, the top one here, I think I see it, yeah. So you can see how this mats up and it gets everywhere. But this, if you put it under a microscope, it looks like almost like sausage links. So that's the nature of this particular type of algae. And it gets everywhere. It plugs up diffusers. It does. I mean, it's very invasive to the system. The second one is actually the plankton algae, often called pea soup algae. It's basically embedded in the water, and you don't see any clear water. It's just basically all green. This algae is the most commonly seen around wastewater lagoons. Plankton algae is also the most resilient and the hardest algae to control. And let me see if I can get my pointer going. As you can see here, it's very, very thick, very, very concentrated, and that's what it looks like under the microscope. Char algae, or macroalgae, is often called skunkweed. Whenever you break it apart, it smells like a skunk, or it has a real heavy, musky smell to it. And it looks like it grows from the bottom of the lagoon, but it actually doesn't. But that's an actual picture of it right here. And you can see it's got the little segments like this. Char is very treatable and can be easily controlled. Char is more common in recreational ponds and lakes, but has been spotted in some wastewater, and we've seen that several times this year actually. Why is there so much algae? And what makes algae grow so fast? Algae is just like any other plant on earth, and it's no different really than like growing crops or seeding your lawn or actually fertilizing your lawn. Algae basically needs two things to grow. It's basically ammonia and phosphorus. If you got ammonia and phosphorus in your system,
that's exactly what happens. You just get a infiltration of actual algae, and you're just feeding it. And they like all farmers, they add nutrients like ammonia, nitrogen, phosphorus to make their crops grow and their lawns plush. So sometimes a lot of runoff water, from not necessarily from around your lagoon, but from other places, if you have a combined system, all that nutrients gets into your system and then it goes right to the lagoon. And that's what actually creates the algae blooms. Ammonia nitrogen is the most popular. That's what it loves. And just like bacteria also need ammonia. So in order to, if you have a BOD for every 100 parts BOD, you need 5 parts ammonia. So if you actually have a good biomass, it'll usually consume most of your algae or ammonia. And then phosphorus. Usually we see even the lowest form of phosphorus, even 1, will be enough to actual feed algae. And usually you can kind of tell when you go out if the algae is super dark green, that's usually because you have a high phosphorus number. And then sunlight is the third thing that algae needs. A lot of times, well, it's just like any other plant, it's creating photosynthesis. So the less sunlight you have, the less algae you'll have. How does algae affect your lagoon? It creates high dissolved oxygen. So the byproduct of algae is actually DO. It gives you a high DO in your system. It also creates a high pH. Basically what it'll do is create that sensation of the high pH. I've seen it as high as 9, 10, 11, so, well, not necessarily 11, but I've seen 10 before, so. And it creates high TS, so it's actually got a double-edged sword. So you're going to have a high pH and a high TS, but it is going to actually generate some actual DO. If you have a facultative lagoon, actually you rely on some algae to be able to give you the dissolved oxygen you need to be able to keep a substantial biomass. Because without, the bacteria also need oxygen. The more oxygen you have, the more the biomass, the greater the biomass you can create and hold. Now we know how to identify what type of algae you have, and we know what makes the algae grow and thrive. We need to know how the algae affects your lagoons. Now it's time to learn how we control algae in your lagoon. We can control it chemically. We can control it with like a dye that has a filter. We can control it with all different types of like chelated copper sulfate, things like that, which we'll get into in just a minute. And you can actually control your algae physically, naturally, and also mechanically. Copper sulfate is my least favorite because the chemical used for the algae to control algae is actually very toxic, and you never want to use granular copper sulfate and only use the chelated copper sulfate. Copper sulfate is a heavy metal and it's toxic to not only the algae but to your biomass as well. The reason I say granular because the granular actually goes down into the actual sludge and it oftentimes never gets released. The thing you really need to know about using chelated copper sulfate, the lower the pH, the more efficient it's going to be. So if you look at night, if you were at your lagoon at night, you can actually see a drop in algae or a drop in pH and a drop in DO. That's because when it's nighttime, they don't actually produce, they don't reproduce and they can't generate the high pH or the high DO. But if it's used properly, it's a very effective. And whenever we decide to use copper sulfate, we actually mix it with a surfactant. And this surfactant basically gives the chelated copper sulfate the ability to float, and it stays in that upper zone because the upper foot or so of your lagoon is where the most and the highest concentration of algae is always going to be. The lower you go, the less algae you have because the less sunlight you have. copper sulfate can be an effective treatment if used properly. The key to using chelate copper sulfate is always using the surfactant and know what your pH of the water is. So just like I said previously, we really do need to watch the pH. Sometimes we'll actually use like vinegar or something like that to be able to drop the pH if it's a concern, if we can't, fight it at night like that. The surfactant is always the key. It keeps that active ingredient in that kill zone, so you're not much of it's going down into your sludge. We often use blue dye that has a UV filter. Now you can go to Buckeyes in different places and get blue dye, but if it doesn't have the UV filter, it really isn't going to do you any good. So you must use a blue dye that has a UV filter to best block out the sun. The whole point of the UV filter is to be able to block the UV rays that it needs to be able to create photosynthesis. Yeah, basically since it can't create photosynthesis, it can no longer survive, and it limits your algae's growth rate. By using blue dye, the UV filter is one of the least expensive treatments. Blue dye is very effective, very inexpensive. And again, when you apply blue dye or any kind of dye, black or whatever, and it has that UV filter, you always want to make sure you use a surfactant to keep it in that upper column too as well. The surfactant keeps the blue dye at the top. You don't have to use as much blue dye, and it actually does a better job filtering out the UV lights. Physically, reduce or remove sludge. By reducing and removing the sludge buildup in your lagoon, you will reduce the amount of ammonia and phosphorus available for the algae to essentially shutting off its food supply. Sludge buildup in lagoons is septic and anaerobic. The byproduct of an anaerobic process is ammonia nitrogen. So if you have a lot of sludge in your lagoon and you don't have aeration and you don't have it's a facultative system, all that is septic in the bottom, and the byproduct of a septic system or anaerobic system, you're going to generate a lot of ammonia, which is the food source for the algae. And that sludge will also release some of that phosphorus too, and which is also another food source. So sludge buildup in your lagoon reduces retention times, increases short circuiting, increases load and oxygen demand, and it affects your pH. Anything septic or anaerobic always has that tendency to be on the acidic side. Reduces alkalinity. Why alkalinity is so important: if we want to remove ammonia, you got to have a baseline of 50 alkalinity, and for every 1 ppm of alkalinity or ammonia you want to remove, you got to add 7.5 points of alkalinity to that, or parts per million. And it creates toxicity. Increases fecal coliform count. Oftentimes we see an increase in fecal coliform because a lot of times if you reduce your retention time, it basically creates a situation where you are not fully digesting the food or the BOD or the solids coming in, and that's why the fecal coliforms go up. Because basically fecal coliform is an indication of improperly processed waste. Increases NH3, BOD, and TSS, which we just talked about. Sludge, the byproduct is ammonia, and if you don't have the ability or if you don't have the time necessary, you're not going to be able to break down BODs and TSSs properly. It increases algae and duckweed because of the ammonia. And just like algae, duckweed also feeds off ammonia and phosphorus as well, and it creates odors. And when floating sludge rises, it definitely is an odor issue, and it has many, many other negative effects naturally. So just like I said earlier, when you algae basically feeds off of ammonia and phosphorus, so does bacteria. So bacteria can also be a natural form of treating algae. By adding bacteria to your lagoon, you're increasing the biomass, which will reduce your sludge and outcompete the algae for its food source. Bacteria consume NH3 and PO4, which is phosphorus, of course, to grow and multiply. Whenever adding bacteria, it's important to test and control your pH. The best pH range is between 6 and 8. When you get up above 8, the bacteria slow way down and they can't function as well. Same thing if you get less than 6. Mechanically, aeration, and algae consume CO2, which is carbon dioxide. Aeration and mixing of the wastewater can strip the CO2 from the water column, and the aeration can also accelerate the biological process by creating more active biomass that will consume the nutrients that the algae needs. So aeration can actually help reduce the amount of algae. It won't completely eliminate it, but it will actually help reduce it. I'm going to back up here just one more. I don't have it up here because we've recently just started using it, and that is the ultrasonic equipment. Basically, it's a floating device out in your lagoon, and it produces ultrasound. And the ultrasound interferes with the algae's ability to reproduce. It ruptures cell walls, and it basically kills it, and it sinks to the bottom, and it becomes sludge, just like you would any other way that you control algae. But my actual experience with that is, and like I said, we just started using it this year. I have a customer that actually has a lot of nutrients in their wastewater. We put 3 of these in, 2 in one lagoon and 1 in the other. It's not a quick fix to me. It takes a long time. It's almost like you have to start out with a low algae count or low TSS, and then actually what it'll do, it will actually act as a deterrent. And in this particular case, we still have to use like a blue dye. We quit using any copper sulfate, and that's been able to actually help us control our algae very, very well. So is it a quick fix? No, it takes months and sometimes years. I do have another customer in Ohio that uses them, and he said it does work. It does a very good job for him. And he said that it took almost 2 years to get to the point where he actually realized a difference. So does it work? Absolutely. Is it going to be the only fix you have to have? Maybe not, but it is possible. So I wouldn't rule it out completely. They're fairly inexpensive as a capital expenditure, and they take up very, very little electricity. And they're easy to install too. The only other thing, when you have the ultrasonic equipment, you have to go out, and there's a transducer on the bottom of this unit, and you have to clean it periodically, monthly, it really depends on the wastewater, and it depends on if you've got an aeration system. Aeration actually interferes with that particular technology, but we found it to be very effective.
But we are doing a pilot on it.
Oh yeah, that's right, I forgot about that. Yeah.
With that to see.
Yeah. I'm very interested to see how that works for him.
Have you guys ever used that, like the ultrasonics in an effluent channel, or is it just lagoon-based?
No, it's all lagoon based because it takes so much time, and it's about, and you can correct me if I'm wrong, but I'm pretty sure it's about stagnant water. If it's moving water, I don't think it'll give it you know what I mean? Yeah, it won't. Yeah. Controlling discharges. Now, how does controlling my discharge affect algae? By holding your discharge, you exhaust the nutrients that the algae need to multiply. So talk about this a lot, actually. If you have a lagoon, you have valves that you haven't used. It's always a good practice to exercise valves. But a lot of times we have like a primary, secondary, and a tertiary lagoon. So if you hold the primary, the longer you hold it in there, it gives you the ability to keep reducing the ammonia and the phosphorus that the algae need in the secondary and the tertiary. So the actual, another benefit is, as you can see in this picture, let me see if we can get my board. We have a low, and then we have a couple of these up higher. But you can crack the lower one, and like I said earlier, the heaviest concentration in algae is always going to be in the upper foot to 2 feet. Below that, it's very, very little algae. So if you hold as much as you can and you transfer as low as you can to the secondary, you're basically not going to be transferring much algae over to the secondary. So, and then it's easier to control it that way. Using a varied depth valves, you can choose the depth of the water that you want to draw from. The most concentrated algae is always in the upper 8 inches of your lagoon. Controlling discharge depths between lagoon cells is one of the least expensive and most effective to control methods of reducing algae. Yeah, the one thing you want to be sure when you're using this particular method is when you discharge, you don't want to disrupt the anaerobic, especially if you have a facultative lagoon, because if you drop it too much, what you'll do, even in a facultative lagoon, there's an aerobic zone. So if you put that aerobic zone right on top of your anaerobic zone, you're going to kill all your anaerobic bacteria. So you want to keep it at least a couple feet to 3 feet above the actual sludge. You never want to drop your lagoon to the point where you see sludge. One reason we don't want to disrupt the anaerobic process because it's the most efficient system for removing BODs. For each pound, this is just some simple facts about algae. For each pound of algae produces 1.6 pounds of oxygen on a normal sunny day. 2/3 of all wastewater lagoon effluent violations are due to algae overgrowth. For each 1 milligram per liter of algae suspended solids, it results in a 0.5 milligram per liter CBOD. Algae uptakes oxygen in the absence of oxygen or sunlight. So like when we run our BOD test and there's a lot of algae in that water, if you're using, out of that 300 milligram, if you're using 50 of it, you could be adding 0.5 milligram per liter BOD, which would be a false BOD because it's technically not considered, I say a false BOD, it's still BOD, but it's creating a false BOD because it's uptaking all that oxygen. So, especially when it's in the dark, because we always store our BODs in an incubator that's not lit, so that algae is always going to be dying, and when it dies, it's actually going to uptake more oxygen as well. All right, we're going to move on to duckweed. Duckweed and watermill weed control. So we're going to talk a little bit, how do I know if I have duckweed or watermill? And does it really matter? Duckweed identification, basically we're going to look at how we identify or separate the two, one from the other. So the duckweed, this is a very good picture of it because it has that root system. And millweed does not have a root system at all. So if you pull this up out of the water and you can see some of the root systems here, that's what duckweed looks like. That's how you identify it. And then duckweed is small, free-floating aquatic green plant with one or more leaves and a small visible root. Now watermill, you can see you have duckweed and watermill in the same picture here. Watermill is much, much tinier. It doesn't have that root system like duckweed does. So I always tell, whenever somebody calls me and wants to know what they have, I basically tell them duckweed is the size of the eraser on a pencil. Millweed is more like the lead in the pencil. So watermill is a small, free-floating aquatic green plant with no root system. Both are considered one of the fastest growing plants that can double their mass every 2 to 3 days. Both can grow in temperatures as low as 34 degrees. Both can survive pHs as low as 3 and as high as 10. Very resilient. Both reproduce by buds called terns. The terns break off from the parent stem and sink to the bottom, and the starch-filled terns rapidly begins to metabolize, causing the structure to float back to the surface and grow into duckweed or watermill. Why is duckweed and watermill a problem? A dense cover of duckweed or watermill on your lagoon will reduce the wave action of the lagoon needed to produce oxygen. So if you have a facultative lagoon, one of the things it relies on besides algae for oxygen is the actual wave action. So if you don't have any wave action, you're not going to get nearly as much oxygen in your lagoon that you need to, to be able to create that biomass. So wave action is very, very highly dependent upon in facultative lagoons. And if you have a thick cover of duckweed or millweed, you're not going to get that. So duckweed and watermill also reduce the sunlight available to the algae that is also produces oxygen. So often you'll hear some people, everybody's always on the fence about duckweed and algae, and duckweed's good, algae's not good, but they both have a plus. So often I say I don't really mind a lot of duckweed in my final, because it keeps the algae down, which is a natural way to control algae, of course, by actually blocking out the sunlight. The only trouble with that is it takes away all the benefits of getting the oxygen. It actually makes your DO lower. So it actually creates a septic condition, which will also drop your pH. Low DO will also reduce the ability to reduce BOD aerobically. Low DO and septic conditions will interfere with the lagoon's ability to fight pathogens, and this will result in an increase in your fecal coliform count. And that's very true, because if you don't have enough oxygen or sunlight in that final, it actually will increase your fecal coliform count. So if you got a high fecal on your effluent and you got duckweed there, that's usually the indicator that that's why it's there. What makes duckweed and watermill grow? Duckweed and watermill, like other plant-based life forms, take up nutrients like ammonia, nitrogen, phosphorus, and sunlight. So that's what it takes to make them grow. Okay, how can I control duckweed and watermill? Duckweed and watermill like stagnant water. So anything that moves or disrupts the water, anything that will, like barriers around, like trees or fences or anything that reduces wind action, that's actually going to indicate or actually help the duckweed even grow more. Like a fountain or any kind of moving water, anything like that, it kind of pushes it away. It still will probably still exist, but it deters it from becoming more aggressive. Controlling the nutrients by controlling nutrients that enter the lagoon, like ammonia, nitrogen, phosphorus, over fertilizing, and even livestock. If you have livestock near your lagoon, or if you have a lagoon system and you have livestock nearby that rainwater gets off into your collection system, that's very, very high in ammonia, nitrogen, and or sludge buildup. Adding bacteria will help control the nutrients, but I often tell everybody, don't expect it to control your actual duckweed or millweed, because it simply won't. You can outcompete the nutrients, but it doesn't take much nutrients to grow duckweed and algae, or duckweed and watermill. Manual removal of duckweed. How can we control the duckweed and watermill? It is an option, and it actually makes for a very good fertilizer. I've seen different guys go out and try to remove it, and they let it just basically compost down. It's very nutrient rich. Some people put carp in, grass carp, and that's kind of it's another natural way of doing it. But there's different types of carp, and then whenever they reach a certain point, you have to add more carp. So the chemical treatment, there's basically only two types of chemical I ever recommend, and that's US EPA approved, and that is sonar. Sonar is very expensive. I'm gonna grab a drink of your water, buddy. Thanks. Sonar is very expensive. The thing about sonar is you have to be able to hold that water. They say 15 days. I always tell everybody 20 to 30 because the longer you hold it, the better the kill. And the sonar is just like anything else. You want to put a surfactant with it so that it stays up in that zone, the kill zone for the duckweed and milkweed. Now, when you're using these two types of chemicals, if you have millweed, you have to use almost twice as much. So, if you do get the chemical and you try it, follow the directions on the back very closely. And there is some restrictions on how often you can apply them. So, sonar you don't want to apply very often. Sonar is very, very effective, but a lot of people cannot hold that water that long. So, propeller would be the next one. And then propeller is one. It is a contact herbicide and it also is an absorbent. So it's actually, sonar is just an absorbent only. So if it comes in contact with the product, it'll kill it, or if it absorbs it, it'll kill it. But 48 hours and propeller is out of the system. So I always recommend holding that water for 48 hours and it completely is entered at that point. So in other words, whatever it's going to kill is going to kill in that first 48 hours. It's very inexpensive compared to sonar, but you have to do multiple applications, and it's not recommended to do applications any closer than 30 days apart. So no matter if you got duckweed or millweed or algae, it is always something that everybody discusses and some people have a major problem with. And that's my presentation on that. Any questions? Great. Thank you.
We're going to take a 5-minute break to get ready to transition and give Robert a
does. Yep, it's working.
Okay, we'll get started with the last presentation for today with control strategies for wastewater lagoons with Robert Risley, Water Treat Tech again. Thanks.
All right. Everybody already knows who I am, so I'll skip the introduction. The control strategies for wastewater lagoons. I've done this probably about a year or two ago, but reason I did it was because a lot of people, I go to a lot of different places, and I actually observed a lot of different things, and I thought it was just suitable to put something together to help everybody to get the information out so everybody can have some different ideas on how to control, have control measures in their lagoon to do different things that they want to accomplish. So wastewater lagoons were one of the first wastewater treatment systems ever designed. And why do you think lagoons were the first wastewater system design or treatment they had? Was because they're easy and cost effective to build, simple to operate. Now, some people may argue that point, but consider it really simple compared to a lot of other technology. Most effective or efficient treatment system for wastewater. If your lagoon is designed properly, it is very, very efficient, and it can actually do a very good job of BOD reduction and TSS reduction. The three variables that affect your lagoon performance, there's a chemical influence, a natural influence, and physical influences. All three of these is going to affect the way your lagoon operates and how you operate your lagoon. Loading. Lagoons must be sized correctly for the loading that they incur. Whenever the engineers set up the lagoon and design it, it's all based off of population density. It also takes in consideration any industry, and it also takes in consideration future growth. As we all know, a lot of the industry that comes into a community, they can't actually set up shop until we know that your system is able to handle the loading that industry is able to put on you. So designing a lagoon system is very important from the standpoint of actual how your city is going to grow and its potential to add on and to either residential wise or industrial wise. Another chemical influence is pH. pH affects the biomass. The best pH range is 6.5 to 8.5. Algae raises the pH, and septic waste lowers the pH. pH is it also has to do with the amount of alkalinity, which we'll get into a little bit here. And alkalinity is necessary for nitrogen removal. The baseline of 50 and 7.5 milligram per liter alkalinity to remove 1 part per million ammonia. And then a lot of people, I very often see anybody doing alkalinity, but alkalinity is very important. And a lot of times, the best way to reduce ammonia is through nitrifiers. The nitrifiers that's their claim to fame. That's all they do is consume nitrogen. But if you don't have enough alkalinity, you're basically, tying their hands behind their back. And there's a lot of different ways to add alkalinity, even ways to add alkalinity without raising your pH. But typically the two go hand in hand. Dissolved oxygen. The key for a lagoon to remove BOD, TSS, and ammonia and sludge is all about oxygen. Oxygen also comes from algae, and wind action aerates the lagoons. Salinity and toxicity. A lot of times we'll see manufacturers, they use a lot of chemicals. These chemicals are salt-based. Some fertilizers are even salt-based. And then you also have some toxicity that can be released from like cooling towers and things like that. So it's salinity and toxicity will actually deter your biomass. The more salinity in the water, the less effective the biomass can be. So direct effects of the biomass ability to reduce BOD, TSS, and ammonia and sludge. So if you're constantly got this stuff coming into your system, it's actually going to basically result in an increase in sludge buildup. Sunlight makes algae grow, heats up the water, and strengthens the biomass. That's something else too. When you're looking at your lagoon, a lot of people, we talk about adding bacteria and different things and to be able to reduce sludge. Well, it's only going to happen during the summer months. So when the bacteria reach temperature, or the water reaches about 50 degrees, most of your bacteria is shut off by then. So every 10 degrees drop in temperature is reduces your efficiency of the bacteria by half. So temperature of the lagoon and the operation in series or parallel also has a big effect on it. And then wind, the more DO, raining and snow. Rain dilutes and reduces the retention time and lowers the temperature. Evaporation. A lot of times in the summertime, and right now especially, that's very important because you can actually have no flows. No flows are wonderful things because you're not releasing anything, and you're actually, if you do it correctly and you can adjust your valves, it can result in like seasonal discharges. That makes a big difference when you're trying to permit and you're being looked at for different things. So. But the other downside of it is it concentrates BODs and TSSs. Oftentimes in the summer, when you're not discharging, it'll go stagnant. And I actually tell guys to take pumps and just recirculate a little bit. Just move that water around a little bit. You can even do it from a secondary to a primary or a tertiary to a primary. And some people have the valves in place to do that, and can do it without even to use pumps. Bacteria and biomass. Microbes are the workhorse of the lagoon system, responsible for lowering BODs, TSSs, and ammonias. In conjunction to that, also bacteria need ammonia and they need phosphorus. But they don't really consume a lot of phosphorus, but they have to have the phosphorus to be able to reproduce. The cell wall of the bacteria is all made up of phosphorus, so they utilize phosphorus, but they don't really consume a whole lot of phosphorus. Duckweed and algae, which we just spoke about. Duckweed consumes NH3 and PO4 nutrients. Duckweed also shades your lagoon, causing it to go septic by reducing the wind action and lowering DO. Algae will add DO, but increases pH, and it also increases your TSS concentrations. Lagoon configuration. So when the engineer's designing everything, the design should be to eliminate any short circuiting. Because if you have an entrance here and an effluent here, basically it's going to shoot straight across. But if you stagger them, it actually gives you more retention time. It takes longer for that water to be able to get to the other end and utilize more surface area and volume of your lagoon, which increases your biomass or the ability to reduce your BODs and TSSs. Lagoon hydraulics. Take advantage of gates and valves that allow you to be able to gain control of the flows and the depths of your lagoon. This actually is a very common thing that I see not happening, but if you have gates and valves and you can actually hold one and then release it slowly to the other, you can actually reduce the amount of algae you have. You increase the primary lagoon and its ability to reduce ammonia and phosphorus before it actually gets to the secondary, and then so forth from the secondary to the tertiary. And I mean, a lot of times you got to be careful because I know a lot of systems have a lot of infiltration, and that can, result in tragedy. But if you're, especially this time of the year, the longer you hold it, the better your effluent quality is going to be. Retention times, hold for better treatment, and use control for releases. Control releases are very, very important to me because of the ability to be a seasonal discharge definitely has its advantages. So, I&I, is it a friend or foe? I dilutes, but it also reduces retention time. So if you already have a short retention time, I is going to kill you. But if you have a long retention time, I can actually dilute some of the BOD concentration, that type of thing, and be able to, in some way, be able to refresh your lagoon, keep high alkalinity, that type of thing. Lagoon size, big or small or shallow or deep. We see all different types and sizes of lagoons. And that typically the size of the lagoon is based off of not only the loading that it occurs now, but in the future as well. But deep lagoons, if you have a strong BOD coming in, you want a deep lagoon to take advantage of the anaerobic side of that, because anaerobic lagoons or systems actually are fantastic about reducing BODs, TSSs. But the actual problem with that, the byproduct of an anaerobic process, it generates ammonia. But if you have a primary that's not aerated and you want to be able to control your BODs better, the deeper the better. And then much like a septic tank. But anyway, then it goes to the secondary, and then you want to aerate your secondary so that you can get your oxygen back and you'll be able to strip out some of that ammonia. Aeration and mixing. Aeration types, when to mix and when to aerate. So I see this quite often. A lot of times, we also, if you don't have a deep lagoon, you don't want to, if you have a deep lagoon, you don't want to aerate because you're going to disrupt the anaerobic process. But then the secondary, you want to aerate. But the mixing and aerating, the thing you got to remember about mixing and aerating is that even in activated sludge, the heavier the mixed liquor, okay, the less efficient that the finer bubbles diffusion is going to be. So in other words, and it doesn't matter if it's in a lagoon or if it's in an activated sludge, the thicker the mixed liquor, the less efficient the fine air bubble system is going to become. So if you carry a heavy mixed liquor, you're going to have to generate a whole lot more power to keep that same DO up, because it's definitely not going to be substantial or sustainable. So you want to be, in order to be able to be more efficient, you want to carry a lesser mixed liquor if you have fine air bubble diffusion. But if you have coarse air bubble diffusion, the actual heavier mixed liquor is actually an advantage to you. You're able to get more reduction. So, but that is why we want to aerate and then mix, because if you some aerators, floating aerators, are just mixers. Some of them are actually aerators. We also are a distributor for nanobubble technology, and those type of aeration systems generate micro and nano bubbles. Okay, they're buoyancy neutral. So much like any type of fine air bubble, coarse or medium, as soon as that bubble is conceived, that's where most of the oxygen transfer happens, and the rest is on the rise to the top. So the actual, in a nanobubble situation, it's actually buoyancy neutral. So it's going to stay in the water column longer, and it's going to have that tendency to spread out throughout the whole lagoon and not just in one area. So it's not really about mixing as much as it is actual aerating. So sludge buildup affects the pH. It affects the ammonia, the BOD, and the TSS reduction. The reason it does that is because it simply reduces the retention time you need, because when the engineer designs the lagoon, it's all revolves around retention time needed to be able to take all these in consideration. Sludge buildup. We can talk about control strategies for lagoons we cannot talk about control strategies for lagoons without discussing the effects of sludge buildup. Sludge buildup affects every chemical, natural, and physical influence that affects your lagoon. Sludge buildup in a lagoon is technically your enemy. So when it robs your retention time, it's going to rob the efficiency of you to be able to reduce BODs and TSSs. We actually have a a remote control boat that has GPS, and it also has a sonar on it. And we actually go out in the lagoon, we measure it. It gives us a 3D image of the actual sludge. It gives you the sludge volume. It actually gives you the water volume, so you know what your retention time is. And it actually quantifies the liability. So a lagoon itself is an asset, but the sludge in the lagoon is the liability. Because the reason it's a liability is because it takes a huge amount of money to remove sludge from a lagoon to land apply it, or take it to the landfill if you have that option, or if you don't have the option of land applying it. So sludge buildup, I think you just seen this slide earlier, but sludge buildup in a lagoon reduces retention time. It increases short circuiting. It increases load and oxygen demand. So even if you did have oxygen, it's basically going to rob all that oxygen you just generated. It affects your pH. It reduces alkalinity. Reason it reduces alkalinity because it becomes acidic, and it creates toxicity. It increases fecal coliform. It increases ammonia, BOD, and TSS because you've robbed the retention time it needs to reduce those. It actually increases the algae in the duckweed because it's generating more ammonia and phosphorus for it to grow. It creates odors. It creates floating and rising sludge and many more negative effects. Wastewater lagoons are an asset to the community in handling their waste. Lagoons are very cost effective and require little maintenance or manpower. The sludge in the lagoon, however, is the liability. Lagoons are typically designed for 20 to 30 years, so when your engineer gives you a set of plans, basically he's giving you 20 to 30 year life cycle in that lagoon before you have to either build a new one or actually dredge it out and extend its life. There's a lot of things that go into that as far as helping it increase that life cycle. If they designed a facultative lagoon, you can add aeration to extend it. You can do bioaugmentation. There's a lot of things you can do to help make sure that your lagoon is always going to have plenty of life cycle. And a lot of times we'll do sludge surveys. That's because that tells us the liability side of it. That tells you how much time you got left. Once the lagoon reaches the point that it can no longer treat the waste within the permit limits, the lagoon will need to be dredged out or decommissioned and a new one put in place. A lot of times people look at dredging their lagoons. Once you have identified the quantity of that sludge and you can actually put it out for bids, you can see what it costs. But sometimes it's maybe to your advantage to add another lagoon and then basically use that as your primary and then use the other one. You can actually basically kick the can down the road to be able to reduce that sludge, save money so you can get it done. And then you're able to control your costs a little bit because, to be quite honest, you can almost build a new lagoon for what it costs to remove, a couple million gallons of sludge. The cost of removing the sludge from a lagoon is very expensive and can most often exceed $500,000. It's very important to monitor your sludge buildup to quantify the community's liabilities so they can plan ahead to save money to remove the sludge buildup. And then how do you monitor sludge buildup? You can physically set up a grid along the lagoon, go out, if you want to do it yourself, this is how you would go about doing it. And actually, the Illinois Rural Water actually can do this a lot of times at no cost to you, or at least they can assist you with it. So go out in a boat, measure the sludge in each grid and with a sludge judge, and then record each grid depth, and that way you can calculate the volume. You can have us do it, which we have the remote control boat with the GPS coordinates, and it gives you the sludge depths from your lagoon. And you will receive a detailed report that comes with a topo map of the 3D image that shows the impacted areas of the volume of the water and the sludge in your lagoon. The good thing about that is if you know that you have this area right here that's got the highest concentration of sludge, and if you want to treat it biologically, you focus all your time and efforts on that particular spot. Or if you're going to physically remove it and you can't afford the whole thing to be dredged, you can at least identify what spots where you want to start and get the most amount of sludge out of it. once you know the amount of sludge in your lagoon, you can now plan on how much time you have to come up with a solution to extend the lagoon's life capacity. 3 ways to handle sludge buildup. You can dewater the lagoon and physically remove the sludge from the lagoon and land apply it. And then add aeration to the lagoon, which speeds up the biological process of removing organics. Now the key word there is organics. So if we go out and identify where all your sludge is, you really do need to get a sample of it to identify how much of it is volatile and how much of it is inorganic. So the bacteria is only going to consume organics, that's it. It's not going to touch your sand, its rock, and its grit, and all the other stuff that comes down the line. So it's only going to reduce the actual sludge itself, the organics. Basically, adding bacteria to the lagoon improves the organic removal of solids. Now we're going to get into a little bit of lagoon design. One of the factors must cover in a lagoon design, lagoons are design determines how the operator must operate the lagoon. For example, an operator that will operate a lagoon that is deep much differently than it would if it's shallow. An operator needs to operate a lagoon that is 2 acres much differently than one that is 10 or 20 acres. Lagoon design is a physical variable. Size of the lagoon, like I've mentioned a couple times, it's all based off of loading and population density and actual guesses or estimates of what the future growth of the city is going to look like. The depth of the lagoon will actually be determined by the loading if you have any kind of factories or any kind of industry that has high BODs. Like I said earlier, the depth of the lagoon, the deeper it is, the more anaerobic it's going to be. The shallower it is, the more aerobic it's going to be. In the case, a lot of times people put floating aerators out in lagoons, but if you have air diffusion in the bottom of a lagoon, like I said earlier, the oxygen transfer only happens in the conception of the bubble. That's like 80% of that transfer of oxygen. The other 10 or 20% is on the rise to the top. If you can keep that bubble suspended in the water column longer, you get more efficiency. More oxygen transfer, actually. And it also, the lagoon design actually determines how many numbers of lagoons that you're going to have. There's a plus side and there's a minus side to that. We had a customer that had, he had probably 60 acres of lagoon, but he didn't have much coming in. So he basically didn't have enough food, available to keep a biomass active in his lagoon system. So we actually had to eliminate a lot of them because in order to be able to reduce his high BOD, you couldn't just dilute it away. You had to actually physically reduce it biologically. Layout and direction, taking advantage of prevailing winds. Like I said, a lot of times if you have a facultative lagoon, it all depends upon wind. The more wind you can give that thing, the better the DO it's going to be. Population equivalent we talked about that several times. Future expansions, I&I. If you have a combined system, that will increase the size of your lagoon because you need that to be able to suppress all that high flow whenever you get large rains. Industrial waste in the community, some industrial waste has high BODs and and high CODs. So we have to take all that in consideration because that plant can't actually expand in that area in your community unless your wastewater lagoon is able to handle it. And it's also designed to eliminate short circuiting, which we talked about earlier. So short circuiting is really your enemy because the faster it goes from point A to point B, the less time you have to treat it. Piping and valves to control flow and depth of the lagoon. If you're looking at a system and you're trying to design it, it's always nice to be able to bypass and have different pipes and valves in there so that you have the ability to return water or be able to bypass in case you want to dredge it or drain it for whatever reason. Bar screens and grit and trash removal. I'll tell everybody when they design anything, it doesn't matter if it's an activated sludge system or if it's an actual lagoon, The best money you can spend is on a bar screen and grit removal to remove all that before it gets to your system. Trash and debris is constantly being, it'll clog up diffusers, it'll clog up floating aerators. It really is, it's a negative for everything, because if the bar screens will get the trash out, but you got to have a grit removal to get all the sand and dirt and rock, which you can just, dump it to the side. So, piping and valves. We're going to talk about control flow and retention time of your lagoons. Operators, if your lagoons have valves and gates control the flow from one lagoon to the next, you should be using them. I have seen hundreds of lagoons that have the ability to do this and have these tools available to them, but they simply don't do it. And 90% of them don't take advantage of using them. And if you haven't exercised those valves in a long time, you need to set up a program where you can replace one or two every year. So, because to me, that's very important when operating a lagoon. And this is just a picture that was in the other one, but you can tell he's got different elevations here where he can pull it off at different times and at the speed that he wants to. Why use these tools? You can control your discharge, and controlled discharge has its privileges. The more time equals better treatment. So being able to hold it always equals better treatment. So the longer you can hold that, the more treatment it's going to get, the better your effluent's going to be. Better evaporation rates. And like I said earlier, as we all know, they got a 3-to-1 slope on lagoons. The fuller it gets, the more surface area you have, the higher the evaporation rate goes. So if you can evaporate more water, that's less discharge, less testing, and you have the advantages of becoming a no discharge for that month, and no samples to test. Every month you don't discharge is like reporting a perfect score. If you don't discharge, you don't report anything. If you're ready, or if you're really good at controlling your flow, you can become a seasonal discharge system. We actually had a customer that was it's basically a campground RV park type thing, but there were several, like in the late fall, all the way through the winter, basically there was no flow. And then whenever it come time to renew his permit, they were still wanting to get twice a month testing. And well, my argument to that point was, why would I do that? Because he's already well within compliance, plus he's a seasonal discharge, and I got that dropped. So, so actually it can be very beneficial in arguing a point of better, basically there's no sense in doing more when it's already doing very, very well. Why use these tools? Controlling the discharge not only means to better effluent results, but it also means controlling the effluent from the primary to the secondary. Bypass a lagoon. Sometimes you can actually get to the point where you can bypass a lagoon if you want to. Now, you still have to use your filters, you still have to do everything that's part of your process, but if you have to, you can if something happens to a lagoon, you have an upset situation, you really do need that. If you have to, you can bypass it for that reason. Returning an effluent back to the primary. Oftentimes in the dog days of summer, I actually see it that the primary will go stagnant. It actually kind of produces blue-green algae, that type of thing. By returning that water, you're still creating a circulation. It's not actually just stagnant completely. You actually are able to return that back through the system and freshen it up a little bit. If you have a sand filter, it could mean that you can slowly release for better treatment. Not hydraulically overloading the sand filter means better oxygen transfer and better polishing. So if you have a sand filter at your effluent as part of your process system, I see it quite often actually. People will just turn the valve wide open and just let it flood and go on. Well, that's technically not the way you're supposed to do it, because you're hydraulically overloading your filter. If you give it a low flow and you don't completely flood it, you actually get better oxygen transfer, better treatment of your effluent. So it's able to act as a better filter that way. Bar screens and grit systems, the most important thing anyone can do to make their system operate better, last longer, require less man hours, is to reduce electricity usage. and get better aeration and mixing and better treatment, you need to get the finest bar screen and grit removal system that money can buy. When you are building a new plant or even upgrading an old system, the best money spent is always keeping trash, grease, grit out of your treatment system. This is very important because the grit and stuff like that and the trash is going to interfere with your operating system, and then sometimes the trash gets into your sludge. But the grit and stuff, if you have an activated sludge system and you don't have a grit removal in it, it'll get in all these little nicks and corners and stuff, and where there's not a lot of movement, it'll rob you of your retention time. And before you know it, you'll have a ton of that built up in your system, and it interferes with the ability of your diffusers to actually transfer oxygen. So it's always best to spend that money up front, get that out so your system's much more, it runs much more efficient. And the other thing too, it'll help because land applying sludge, farmers are becoming more and more particular. If it's got a lot of trash in it, they're not going to want that sludge. They don't want that stuff out in their field. So in order for you to be, have more options for placing your sludge, you really do need to get a good bar screen system. Grit will find every corner and pile up in equal or in every quiet zone that you have, and it robs you of retention time and wears down your equipment. Trash will collect on diffusers and plug up pumps and end up in your sludge, and the farmers they don't like trashy sludge no matter how nutrient rich it is. Finding farmers to accept sludge is getting more and more difficult because of this reason. And that's it. Any questions? Yeah.
So when you commented about doing a sludge survey and collecting the sludge samples,
Yep.
the volatiles, I think previously when you've given the presentation, you mentioned a minimum level of volatiles.
Oh, yes.
that
Right.
If you were at or below that really adding the nutrients would not do anything necessarily for reducing sludge.
That is correct. So, so when you're looking at your volatile suspended solids, in your report, it'll tell you your percent of volatiles versus your percent of inorganics. The higher the volatiles, the more successful you're going to be in reducing sludge. And if you have inorganics, which is the opposite of the volatile suspended solids, that's actually not going to change anything, no matter what we do. That will have to physically be removed from the system. We're talking about sand, grit, dirt, anything like that. And then when we sample, we use a core sampler, and we go down and we pull that up from the bottom up, and that's how we get our percentage of volatile suspended solids. So, and then a lot of times when we do sludge surveys, we'll have to look at the percentage of how full that lagoon is. My advice is always when that lagoon is over 50% full, you really do need to be considering removing that sludge one way or the other. So if you can remove if you have a high VSS and if you don't have the money available or you're waiting on funding, it's always nice to be able to add aeration and create more bacteria to be able to help reduce that organic. So when you do have the money or the funding available to remove that sludge, it's going to be of a lesser content. So, and yeah, farmers like the nutrients. They like see, for a lot of farmers, they just basically put chemicals down when they grow crops, and they often don't overlook the organic part of it. So when you add give a sludge to a farmer to put in his field, you're actually putting organics back into his system, so it actually helps his crop growth rate.
Are there any other questions in the audience?
All right. Thank you. Appreciate it.
Okay, we're going to switch over to some operator group meeting, some discussion maybe about some future meetings and possible trainings. I think Jason had some things he wanted to talk about.